So this is the fundamental forces of nature, and what I'm trying to avoid here is ignorance. You know, it's like if somebody in the future, probably somebody writing about why American schools are failing or something like that, and they stick a microphone in your face, okay, and they say, "Hello, what's your name, young lady?"
Lauren.
And what are the four fundamental? Who's your physics teacher?
Murray.
And what are the four fundamental forces of the universe? Right, and they'd be like, "See, right." So we're trying to avoid that we can at least name them and know, what they are. So, here we go. So, and I'm going to have four of them. I'm going to list all four of them, and I'm going to start with the weakest one, and we're going to go to the strongest one. And the weakest one, but also the one that we're sort of more aware of in our day-to-day life, is gravity. Okay, and gravity, like me, is always attractive. Okay. In fact, I look in the mirror sometimes and I'm just like, I don't know how I do it. And it's just something I have to live with. I can't. Nothing I can do about it. Yeah. Okay. And unlike me, okay, gravity is a very, very weak force. And I'll show you just how weak it is here in a moment, right? But it's always attractive. Hey, just go ahead and put it on the counter. Right?
I didn't plan that.
All right, I got you.
Good job.
And then the final thing is that the gravity acts on all mass. Right, so it doesn't matter. It's equal opportunity. Anything that has mass, it acts on. It'll act on a neutron, a proton. It'll act even on a little particle, like photons have mass. Gravity pulls them. Right? Okay, that's crazy. Oh, what? Would it act on a moron? Yes, it would. In fact, it would. A moron is a particle. Okay. And then the next one is electromagnetic force, and that you cannot separate electric force, which is like electrostatic repulsion. I rub a balloon on my hair and it sticks to the ceiling or something like that, right? From magnetic. They can't be separated, and that's because magnets all come from the motion of electric charge. Okay, and then the crazy thing about electromagnetic forces is that it attracts and repels. So for example, the north poles of a magnet will repel each other. These guys will repel each other, but the south poles will also repel each other, but north will attract south. Yes. Yeah, there we have it, right? And the same is true with like charge. Positive charge repels other positive charge, but attracts negative charge. Yes? Kind of a thing, right? And so for this reason, because electromagnetic force also attracts and repels, if you had two galaxies in space, they would exert almost zero electromagnetic force on each other because there's probably an equal number of positive and negative charges in north and south poles, right? And so it would just spend half the time attracting and half the time repelling, okay? And so there'd be no net force. Whereas gravity, everything attracts. And so as far as talking about the universe and how the universe works, gravity is a much more important force for like galaxies and stuff like that. Electromagnetic forces are also pretty strong, and I can demonstrate this, okay? I will show you this. Here I have a piece of metal. I'm going to pick it up with this magnet. This magnet has a mass of 173.08 grams. Okay? Now, the Earth has a mass of approximately 6 million, a billion kilograms. Yes? And I will place this on the floor, right up against the Earth. And the Earth is pulling down on it with all of that gravity. Now I will use the magnet with its 0.2 kilograms. Are we ready for this? The magnet wins. Should we try again? Come on, best 2 out of 3. Oh. Best 3 out of 5. World Series. No, it's always going to win. It's always going to win, right? Yeah? Okay. So yeah, there we have it, right? Okay. Now, the next two forces are nuclear forces. So let's all say this word. Now, here's how we say it. That is how you actually say it. So let's just try it. New, clear, new, clear, new, clear, new, clear. There we go. Isn't that beautiful? Okay. Now, these forces are nuclear forces. That means that they exist in the nucleus of the atom, yes? And they're only important in the nucleus of the atom. And one of them is weak, and one of them is strong. And they are both nuclear forces. And so, when they discovered these forces, the physicists decided to name them. And so they appointed a committee, and the committee met, and they deliberated, and they met for actually a month, right? And they were trying to come up with cool names like gravity or electromagnetic, right? Okay? And the names that they came up with were, well, for the weak one, okay, they came up with weak nuclear force. I guess I forgot to say, electromagnetic force, it only acts on charged particles. So magnets and charged things don't exert forces on neutrons, for example, or a photon or something like that. Right? Now, I know almost nothing about weak nuclear force, but I do know this. It explains certain decays. Acts only in the nucleus. Yeah? There's one last little nugget of knowledge that I could tell you, and then you would know as much as I do. The decays that it explains are beta decays. You can't explain the behavior of a beta decay. A beta decay is where the nucleus is unstable and it burps out an electron, creates an electron out of pure energy and shoots it out, right? Okay? You can't explain it without the weak nuclear force, but I know nothing about it. Okay? Now, what's the name of the other force in the nucleus? It is a strong force that acts in the nucleus, and so they decided to name that other force the strong nuclear force. Yes, yes, because it's strong and it acts in the nucleus, right? Okay? So, this is the deal with strong nuclear force. If you picture an atom, if we take an atom and blow it up to the size of the Rose Garden Arena, first off, you would say, wow, that's a big atom, right? Right? But second off, if you could see the nucleus would be the size of a quarter, it would be the size of a golf ball, something small. It would be very small, depending on what element you're looking at. Some of the nuclei are quite large, actually. Okay? But it would be something quite small. Okay? That's 100,000 times smaller than the atom itself. What's in the nucleus? Protons and neutrons are in the nucleus. Neutrons have no charge. Protons are positively charged. They're crammed in a space 100,000 times smaller than an atom, and atoms are small. So what is cramming all those positive charges together? Don't they repel each other? Shouldn't they fly apart? Doesn't it take a strong force to do that?
Of course.
Yes, what force do you suppose does that? The strong nuclear force is what binds them. So it's like the One Ring in Lord of the Rings, right? It binds them all, and in the land of Mordor and where the darkness lies or something. No. Okay. Nucleons means protons and neutrons. Okay, so protons and neutrons are the set whose members are nucleons. Something are like that. Okay, it's a very strong force, and here's the deal: the strong nuclear force is an extremely short-range force. Now, it is a very short-range force. If we look at the periodic table, there's the periodic table and all of its periodic tableness. Okay, and it goes on, and basically it gets down to like uniquadium and unahexium and all these things, right? Okay, why can't we just keep going? Why are they unstable? Well, they're not stable because the strong nuclear force isn't strong enough. Why is it not strong enough? It's short range, and so as the nucleus gets bigger, it can't hold it because one side of the nucleus cannot transmit the strong nuclear force to the other side. In fact, those big nuclei, like uranium, okay, they're less like a billiard ball and more like a big sort of undulating drop of oil. If you look at nuclear power plants, to get the neutrons to react with the nucleus, they have to slow them down. Why? Well, because fast neutrons just go right through the nucleus. The nucleus is so loosely assembled because the strong nuclear force is at its very limit to hold it in, right? The neutrons can just wander right through the nucleus. You have to slow them down so that they stick to the nucleus, and then the nucleus eats the neutron, and then it goes, ooh, that's one too many, and it goes biff, apart, right? It's like the end of The Meaning of Life, where the guy explodes with the dinner mint or something like that. Isn't that The Meaning of Life? We have a question.